好的，开始录，现在准备开始充电，充电好久。
So let's get started. And please don't forget that our homework 2 is today at midnight. And by the way, do you know how to record this lecture? Because I think there probably is going to be one student studying okay, so unable to come today. Do you have any idea how to record setting? No. Okay. Let's see.
She's already recording it.
Sorry?
She's already recording.
Oh, okay, fantastic. Thank you. Okay, that will be excellent. Yeah. So please make sure it doesn't go out of battery. Okay, so thank you. I'll be relying on you for that. Okay, thank you. Okay, so I plan to come up with the homework 3. Okay, by today midnight as well. And it's not going to do next week, but due 2 weeks from now. And the reason is that I suppose it would be better for us to finish chapter 2, okay, before the homework use. Okay, so you have plenty of time to tune up the whole session, okay, and have a better integrated understanding of everything. And on the other hand, so we have got into chapter 2 for 1 lecture, and I plan to spend another 2 on this, which means that today I will basically, so I will first talk about the energy, okay, the energy method for the wave equation that we have just discussed, and another thing is that I would like to get into 2.4, which is the diffusion on the whole line, okay. Skipping 2.3 for now and leaving that for the next lecture. And the exact reason is that because as you might have already seen, 2.3 talks about a bunch of the analytical methods, okay, for the diffusion equations, which is not I would say, okay, not that direct to understand without an understanding of how the diffusion equations really operate. Okay, so I would like to first introduce how to solve the diffusion equation on the whole line, okay, before we get into the qualitative analysis, okay, for the analytical methods for the diffusion equation. And the last lecture will also systematically compare the wave equation and the diffusion equation, okay, in a more systematic fashion. Okay, so first of all, let's try to close up 2.2, which is another topic that we can get into, which was the energy. Okay? Energy for the wave equation. So last time we have discussed how to solve the equation, the wave equation, which is UTT minus c squared uxx, okay, equals to 0. Okay? And the reason that we would like to discuss the energy is that, well, we find such method is actually called energy methods for a bunch of the linear equations. The energy method, they are usually, it actually refers to something that's related. Okay, the energy is a quantity. First of all, the energy is a quantity. Okay? Just like the energy that you have learned in physics, in your physics classes. It's a quantity. It's a quantity that's related, okay, to the whole system. Okay? It's a quantity that's related to the whole system of the whole system. And since it is a quantity of the whole system, and instead of a quantity that's only related to a small part of the system, that quantity is usually used as an indicator of the system to tell us something about, for example, what can I know overall, okay, for the system. And in this case, the energy is going to be, so don't forget this is a wave equation, right? Which means that I really have a string. Okay, I really have a string that's vibrating. Okay, the string it might be fixed, or it might, let's say, for example, let's say completely free. Okay, and the string might be restricted on a certain interval, or it might occupy the whole real line. Okay, any of these interpretations are okay. But the key point is that the energy, that's something that's related to the whole information of U. Okay, the energy is the information that depends on the whole U, instead of only on a point ux0. That's two different things, right? So you see, ux0 at x0, and the quantity ux0, of course, it represents the displacement, the displacement, okay, of the string at this point, okay, and that's of course one piece of information. However, the energy, let's say E, it depends on the whole U. Okay, so you might be a little bit confused. Okay, so first of all, E is a quantity, right? So that's a number. Indeed, that's a number. And I can tell you that is a real number. And you see, but whatever it takes is the U. Whatever it takes is the U. U is what? U is actually a function. U is a function, at least for one dimensions. And because we know that U is actually a two-dimensional function, x and t, right? Okay. And E is a quantity that is wrapping up the whole bunch of information of U, and compress it and project it to a real number. Okay, so such a process, we call it as a functional. We call it as a function. Okay, function plus a value. Okay. Function. So you might have already heard a lot of, another undergraduate course for that, which is the functional analysis, and that is exactly the same thing. Okay, that's exactly the same. That exactly refers to this type of thing. So you see, the function. What is a function? Function is a mapping. A function always maps. For example, it maps one number to another number, or it maps a high-dimensional mapping or high-dimensional function. If it map a vector to another vector, right? However, the functional, okay, it always maps the whole function. It's a function. So the functional can be interpreted as a functional function. It is a function of functions, which means that the independent variable, okay, within the functional is actually the functions, okay, in the usual sense. Okay, and the functional will take all the information from this function. The functional will take all this information from the function and project it to, in this case, to the function. Okay, and in our case, what we're going to discuss is the energy. Okay, is the energy. So, well, we have talked a lot about how to understand it in the mathematical sense. But now let's try to derive the energy, okay, in a more, let's say, in a more physical sense. Okay. So now let's say, don't forget that we have let's say we're having a string just like this, okay, and the x, it belongs to the whole real line. Okay, so this is a infinite string. Okay, it's an infinite string. And instead of UTT, instead of this form, okay, of the wave function, let's recall that. Don't forget that my c square. Don't forget that my c square actually is what? My c square is actually t over rho. Right, my c square is actually t over rho. T is the constant for tension. Right, T is the constant for tension, and rho is what? Rho is the constant for the density. Okay, the density of mass. So that's good. Okay. And first of all, we would like to derive what, for example, we have been talking about energy. Well, for such a system, for a vibrating string, what type of energy that we can imagine that are involved? kinetic energy. Okay, just like so because let's say for a single point, let's say we are talking about a single point, a vibration of a single mass point that usually involves two types of energy. One type is the kinetic energy, right? The kinetic energy, or we're going to call it as Ke later. What is the other type? What is the other type? The potential energy, right? The potential energy. Okay, the potential energy, which is P. So in our case, actually, the potential is a little bit hard to define because we're going to see that the potential. You see, the potential for a part of the string to move, actually, that is not directly related to the displacement of that point, right? It actually depends on what? It actually depends on tension. It actually depends on the amount of tension at that point. Okay? So instead of directly going into the potential energy, let's say, what about, let's try to derive what is the kinetic energy for the string. So what is the kinetic, so instead of a string, let's say, what is the kinetic energy for a mass point? I have a mass point that is moving. What is the kinetic energy? Ke should equals to what? 1/2 mv squared, right? 1/2 mv squared. Okay. Well, you see, now the whole we are talking about instead of one point, we are talking about let's imagine that the string is made up by infinitely small mass points. Okay. Now we are talking about the kinetic energy for the whole string. Then what should we do? Let's imagine that the string is made up by a small point, 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 small point. Okay. So for example, if I zoom this part out, okay, that's of course part of the string. But this part of the string that it is regarded as one thing. Okay. It is regarded as one small point. Okay. And let's say it's moving upwards. Okay, it's moving upwards. And so the first question is that how do we represent the V? How do we represent the V? It's actually UT, right? It's actually UT. It's actually the UT. For example, if this point is at x0, then then the velocity over here, V actually equals to U x0 t, right? Okay, then what? So of course, V squared is going to be U squared x0 t. That's without any doubt. Oh, sorry, UT. My bad. It's the time derivative. It should be the time derivative. Okay, it should be the time derivative. Okay. Then how do we deal with the m? Okay, but before we integrate, we need to focus. We need to figure out what is the m for this small point, right? What is m for this small point? So we have a rho. So one/2 mv squared, which is that. You see, I have a rho, and but rho is what? Rho is only the density. What is the length? What is the length over here? Let's suppose that the length over here is actually delta x. Okay. Then rho delta x is exactly the m that we are facing right now, right? Okay. Then it's actually 1/2 rho delta x, and then ut squared x0 t. It's something like this. Okay. Then this is the kinetic energy for this small point, and I have infinite many such kind of small point. Okay. Then to collect the whole kinetic energy for the whole real line, then what we need to do is that my kinetic energy now for the whole real line should equals to the sum of all of the energy for each of the small ones, right? Then we're going to write an integral from negative infinity to positive infinity. You see, actually, okay. So let's not go that fast. So before we take the limit, let's say we have such kind of infinite many of small mass point. Then let's say this is my ice. This is my ice point. Sorry, my ice mass point. Okay. So then that means that I'm going to sum up for all of the I. I'm going to sum up for all of the I, and such that 1/2 rho, okay, and then delta x, and then ut squared x, not x0, but xi t. Right. And now, by taking the delta x going to 0, and we'll be having infinite many, such kind of small mass point. Then what we're going to have is an integration from negative infinity to positive infinity, right? And then 1/2 will stay, the rho will stay, and then the ut, okay, is going to stay. Ut squared is going to stay, and then finally it's going to be dx. The delta x actually is now goes into the dx. Okay, so this is the kinetic energy. This is the kinetic energy. Well, before we derive the potential energy, let's see what is the time derivative of the kinetic energy, right? So, which means that you see my ke is what? Is it first of all? It's an integral. It's an integration of what is? It is an integration of 1/2 is a constant, rho is a constant, and ut is actually a function on both on space and time. But I'm only integrating ut squared on space, which actually leaves me a time dimension, right? So actually, my ke is actually a function of time. My ke is a function of time, right? So dke dt can be done as what? Can be done as, okay, so that's going to be d dt, right? The differentiating the integration, 1/2 rho ut squared dx, right? And recall that in this class we can switch the order of integration and differentiation as much as we want. Okay, so that means that it's legal to do. Okay, I'm getting out of rho at negative infinity to positive infinity. Now I'm going to differentiate. I'm going to differentiate d, okay, 1/2 ut squared dt dx. I'm going to do this, right? Okay. Well, what is this guy? dt. What is the time derivative of ut of 1/2 ut squared? Well, chain rule, right? So it's going to be rho, and from negative infinity to positive infinity, the chain rule will first separate a 2, right? So 1/2 multiplied by 2, and then ut, and then the partial derivative of the derivative on the derivative on the direction of t, okay, for ut. So that's actually ut dx. So finally, I obtain something that's actually rho negative infinity to positive infinity utt dx. So good? So good? Okay. Well, what do I know about UTT? What do I know about UTT? Because it's a second order, and second order is always more complicated than first order. I don't want the second order stuff to stay there. So I would like to find a way to get rid of UTT. So what do I know about UTT? According to the PDE, the definition of PDE itself, UTT equals to what? Right. I'm having my rho UTT. I'm having my rho UTT, okay, equals to T UXX. Sounds good? So this actually further equals to T from negative infinity to positive infinity, UT, and then UXX ds. Sounds good? Sounds good? Well, you see, the problem is that, well, okay, I'm still having the second order stuff. I'm still having the second order stuff. But on the other hand, the good side is that you see, this is in the second order, but the integration is also on the spatial dimension, which gives me a chance, okay, to decrease the order of the derivatives involved by integration by parts. Okay, then what we can do is the integration by parts. Therefore, by doing the integration by parts, what we are having right now is actually, okay, now I'm going to do integration by parts. So let me write one more step. Okay, let me write one more step. So from negative infinity to positive infinity, then ut, okay, this is going to be dux. So that's good. I'm just doing integration by parts, throwing the uxx into the integral sign, into the differential sign. Okay. Then by the integration by parts, this should exactly equals to, first of all, t ut ux, and evaluate it at negative infinity and positive infinity, right? And then minus t utx ux dx. This is my integration by parts. So that's good. Okay. Well, the first thing I would like to say is that, okay, this guy is very horrible. I don't want to evaluate. I don't want to evaluate two differentials at infinitely long, at infinity. I don't want to do that. However, I could, let's say, I could play some trick, okay, to get rid of that problem. And the trick is that, you see, don't forget, in the last class, we talk about the speed. We talk about the speed, okay, of information transfer. Okay, and causality, right? Which means that, you see, x and t for anything that's happening over here in the initial condition, okay, then it can at most, you see, it can at most, okay, affect this much. It can at most affect this much when time evolves. Okay, this is called the information column. Okay, this is called the information column. Okay, and so anything that starts from x0 over here, anything that starts from x0 over here, okay, will be any event that takes place at x0 initially, okay, can be at most go to place like x0 plus ct and x0 minus ct, okay, after some time t. Which means that if my initial condition, okay, has a, okay, so in mathematics speaking, that means that if my initial condition has a so-called compact support, if my initial condition has a compact support, which means that my initial condition, let's say, it is strictly it's strictly constrained, okay, on a finite interval. Consider finite interval, which means that, let's say, initially my phi x and phi x, my phi x and phi x, okay, if my phi x is something like this, and my phi x is something like this, which means that they are only non-zero, okay, on a finite interval. And if I go longer and longer and longer and longer, they will be zero everywhere else. Okay, it's only supported. It's only supported on from A to B, okay, on a finite interval. If that condition holds for both of my phi x and phi x, what can I say about the solution at t? What can I say about uxt? If initially the initial position is only non-zero in a finite interval, and the initial speed is also only non-zero in a finite interval, what can I say when these things propagates on time t? What can I say? It should at most affect also a finite interval, right? Because anything, because of what? Because initially everywhere was zero, right? Everywhere was zero. Everywhere else besides this finite interval was zero. And if you want to change that, that means that the pulse, the wave, should travel to that place to change this condition. But the wave is propagating with a finite speed, which is c, right? So that means that, okay, if my phi, so a little bit, so a more mathematical, rigorous way to speak this is the following. Okay, so let's say, proposition. Okay, so if phi x and phi x satisfy that, okay, satisfy that, there exist A and B, okay, on the real line, such that, okay, for any x be larger than b, larger or equals to b, let's say for any x that's larger than b, and any or any x, it should not be or, okay, and any x that's smaller than a, we have phi x and phi x equals to 0. So this is the so-called compactness, the compact initial condition, which means that it's only non-zero on A and B. Okay, my phi x and phi x, they are only non-zero on A and B. That means that this non-zero, the information or this non-zero part, you will propagate, but it can only propagate with a finite speed, which means that after some time, the non-zero part can only be expanded by 2ct, right? Because you see, initially, whatever happens here, right? Whatever happens here can only affect the places any places within this column. Okay, so if I have that, then uxt satisfy that. Okay, uxt should satisfy that. Okay, uxt equals to 0 for any x be larger than b plus ct, and for any x that's smaller than a minus ct. So that's good. Is there any question about this proposition? Originally everywhere is 0. Everywhere was 0, except for this finite interval. Right? So what happens over here? What happens within this interval? They will propagate. One branch on the left and one branch on the right. But the propagation only takes place in a finite speed. Right? So it can only change the non-zero state, the non-zero condition in other places, okay, within a finite speed. So after some time, we can say that it can at most affect the solutions within A minus CT and B plus CT, because the waves, it can only propagate in the speed of c. So it's good. So if I have that compact, so what does that give me? That gives me that for this type, okay, if my initial condition, satisfy this, then what can I say about uxt? What can I say about uxt? what can I say about u xt, okay, evaluated at x equals to positive infinity or negative infinity? What can I say about that? That should be what? That should be 0. Right? Why that should be 0? Because initially it was 0, right? Initially it was 0. The wave, okay, the strain at negative infinity and positive infinity, initially they were 0, right? And the non-zero part is only propagating within a finite speed. So within the finite time, the wave can never reach the infinity, right? Within the finite time, the wave can never reach infinity. It can only propagate to the left or to the right within the finite speed, which is c. Okay, sounds good. Okay, so the uxt is going to be 0. So same reason, ux, okay, xt, when x evaluated at positive negative infinity, this is going to be 0. This is also going to be 0, because negative is 0, right? And things around negative, things around infinity is also 0. Okay. Well, same reason for ut, xt. Okay, x evaluated at positive infinity, right? Of course, this is also going to be 0 because they were 0 and they will keep going to be 0. Okay, in any of the finite time. Okay, in any of the finite time. Okay, so what that gives me that is what that gives me is that this guy. Okay, now if I have a compact initial condition, if my initial condition phi x and phi x, so if my satisfy that they are only non-zero within a finite interval, then I can safely say that this guy is going to be 0. This guy is going to be 0, okay, because they are exactly evaluated at negative infinity and positive. Let me stress again, okay, this is not always true. This is not always true. It only works, okay, this only works for a compact initial condition. Okay. On the other hand, this is actually a rather convenient way for us to discuss energy, because you see, what would the energy be if there are vibrations, and actually vibrations at the same amplitudes on the whole line? What would the energy be? Here I have some vibration, keep going, keep going. Here I have some vibration, keep going. They are at the same amplitude. Here I also have some vibration, keep going, right? And at the infinity, I also have some vibration, keep going, right? Then how would you imagine for the energy? It's going to be infinity large, right? It's going to be infinity large, right? So if you want to discuss a finite energy on an infinite line, okay, probably assuming the vibration is constrained within a finite interval, that's probably a better way to pose that problem. Okay, so this is going to be 0. Then you see what we're having over here. So to conclude a little bit, don't forget that we were talking about the time derivative of the kinetic energy, right? So now we arrive at something like, let's say, negative t, okay, from negative infinity to positive infinity, utx, ux, dx. Well, that seems to be that seems to be something that's not much better, because I still have a second order. But don't forget that initially, you see, this guy, utt, this guy, was actually what? Was actually the time derivative of 1/2 ut squared. So what can you say for utx, ux? What can you say for utx, ux? It's actually, okay, the time derivative, okay, of what? It's actually the time derivative of 1/2 ux squared. It's actually the time derivative of ux squared. Oh, sorry, let me erase this. Okay, d and dt. So far so good. So far so good. And again, I am switching the order of integration and differentiation. And so what I get is actually d over dt, okay, and then the integration from negative infinity to positive infinity, okay, negative t over 2, okay, and then ux squared dx. Is that right? Any question? Sorry, say it again. Oh, sorry, you're right. You're right. The square should be inside. Yeah, you're right. You're right. Good. That's fine. So is it good? Okay. Well, you see, this is d over dk. Right. So let me just simply put everything together. Right. Okay. Let me just put. You see, here I'm having a d something over dt. Here I also have something like d something over dt. Right. So if I write down everything again, so this basically tells me the following. This basically tells me the following. Don't forget what is my KE? My KE is defined as the integration of 1/2 rho ut squared, right? Here it is actually, so if I put everything together, so that tells me that integration from negative infinity to positive infinity, okay, so 1/2 rho ut squared dx, okay? Don't forget, this is my kinetic energy, okay? And then it's this guy, then the derivative of this guy plus the derivative of the integration from negative infinity to positive infinity dt over 2, okay, ux squared dx. This guy equals to 0. This guy equals to 0, right? So if I call this guy to be something like, if I call this guy, okay, to be something like another thing, let's say, I don't want to reveal the answer that quick, but let's say this guy is something like A, okay, at A. So this equation basically tells me that dke over dt plus dA over dt equals to 0. Is that right? What can we derive from this equation? Ke plus the A should be what? Right? So because this basically tells me that dke, okay, dke plus A over dt is what? Is 0. One more step that tells me that ke plus A is a constant. In the physics system, the kinetic energy plus something is always a constant. What would you guess? What would you bet for that something, for that constant? What is always a constant without any dissipation or without any friction, without any friction? The total energy is always a constant because there's no dissipation of energy right? So we will guess, okay, we don't know yet. We will guess the constant over here is the total energy. We will guess the constant as the, well, I'm guessing, okay, I'm guessing, okay? I'm guessing the constant as the total energy. Well, if the constant is the total energy, what do you say about A? A should be the energy, right? Because again, without any loss of energy, then the kinetic energy plus the potential is exactly the total energy, right? So I'm going to guess my A is the potential energy, okay, the potential energy, and let me call that to be my P. Let me call it to be my P. Okay, so now, first of all, so to summarize what we have deduced. Okay, to summarize what we have deduced. Okay, so first of all, we have derived. This is something that we have very solidly. Okay, this is something that we derive from scratch. Okay, which is that the kinetic energy of the whole string, indeed, it equals to the integration from negative infinity to positive infinity, 1/2 rho ut squared dx. So far so good, okay? And based on the conservation law, based on what we understand about the physical system, okay? Now we are guessing, okay? We are guessing this A. We are guessing this A, and it is exactly our potential energy, okay, which exactly equals to the integration from negative infinity to positive infinity, 1/2 T ux squared dx. Let me stress again, okay, we don't know this is the potential energy yet. We're just trying to use conventionally what we understand about the physical system, okay, to guess that it should be the potential energy, because the sum of the KE and the PE should always be a constant. And here we have just derived that the KE plus the A should be the constant, right? How do we show that this is indeed the potential energy? Well, to strictly show that, it might take some time. Okay, it might take some time. But I would like to tell you there is another way to there's a way to see this actually in a very convenient manner, which is that you see what should the potential be related to? What should the potential be related to? Of course, first of all, it should be related to the tension, right? The tension is related to T. The larger the T, the larger the tension, right? Okay, so T is here, of course. The larger the T, the larger the tension. That is right. That is indeed true. Okay, but how do I explain the UX squared? How do I explain the UX squared? Well, we also know that you see UX. That's something that's related to. According to our derivation of the wave equation, UX is actually also related to tension. But how do I say that it's something that's directly related to the potential? Well, you see, here everything. So first let's come to an extreme. Okay, if there is no vibration, what should it be? What should it be like? If there's no vibration at all, my U should be constantly 0, right? My U should be constantly 0. That means that you see, okay. First of all, this is of course a strain on an infinite interval. But on the other hand, when I am taking a segment of this string, let's say this is my A, this is my B, okay, then what is the length of the string over here? Just B minus A, the L equals to B minus A, right? Now, imagine that I am pulling this string. I'm pulling this string such that the string, the small mass point on the string, they are deviated, okay, from its original location. Okay, so now let's say I'm having something like this. This is my after my pulling, my manipulation of this string. Okay, again, this is my A, this is my B. My X equals to A and X equals to B. What is the length of this part? What is the length of this part? How long is that? How long is that? It's actually longer than B minus A, right? Why is longer than B minus A? Why is longer than B minus A? Because the shape is changing. The shape is changed during the vibration, right? It is exactly, so if there's no shape, if there is no change of the shape, that means that because don't forget that in our assumption for the wave equation, there's actually an assumption that the string can only vibrate in a vertical fashion, right? Which means that the mass point over here is actually should correspond to this mass point, and the mass point over here should correspond to this mass point, right? So, which means that if I am manipulating, if I'm pulling the string, actually, okay, all the mass points between A and B, okay, they stay here, they exactly stay here, stay within A and B, right? But the whole string is becoming longer. The whole string is becoming longer than the B minus A. And it also, the shape is changed. So here it produced a tension. And we are not going to argue, but I'm going to directly tell you that the potential is actually directly related to how long. Okay, the potential is related to how much longer is the string compared to its natural position, or sorry, compared to its relaxed position. Right? How much longer is the string compared to its relaxed position? Because if I'm pulling the string longer and longer and longer and longer, tension is going to become larger and larger and larger and larger. Hence the potential. Right? Hence the potential. Okay, I can't prove that to you in 5 minutes. Okay, but this is something that I'm trying to argue intuitively. Okay, the longer the new shape after when I'm pulling the string, then the larger should it be for the potential. Okay, so are we good? Everybody okay with this point? Now we can talk about let's say when we are talking about the potential of each of the mass point. We just need to look into, okay, again, let me try to zoom in this mass point. Okay, now it is about, okay, how long that this part, how much longer that this part of the string, okay, is in length compared to its natural state, which is exactly like this. So initially this was what? This was delta x. Now, what is the length? What is the length of this part of the string? Okay, so this is my delta x. So this part should be what? Delta x multiplied by ux. So far so good. So this part is what? It's actually delta x multiplied by square root of 1 plus ux squared. So far so good. So far so good. So the enlonged part of the string should be exactly, okay, this guy, the length of this guy minus this guy, right? So which should be the enlonged length, okay, should be exactly be, okay, delta x of square root of 1 plus ux squared, okay, and then minus 1. Then it's Taylor experiment because of what? Because we are, don't forget, there's another assumption about the wave equation, right? That was that our wave equation is actually vibrating in a very small fashion. Everything was so small, everything was so tiny, such that I can use, it is legitimate for me to do all of the Taylor expansion and give a truncation and just simply dispose all of the higher order terms, right? Okay, so this is actually what? This is actually approximately, it equals to delta x multiplied by 1/2 of ux squared. Again, what is that? That is the enlonged length of the string in this part. Okay, that exactly equals to the length of this guy multiplied by the length of, minus the length of this guy. Okay, so finally, you see. And don't forget, this is the enlonged length, right? And so integrated that, and also we need to consider the tension. We also need to consider the tension on the unit length. That is the potential. That is indeed the potential, okay, of the whole string. So that's good. Okay. So this is indeed the argument of the energy. Okay. This is indeed the argument of the energy. This is the argument of all of this. Okay. This is the argument of energy. Okay, the argument of energy, and that actually is very useful for us. Why that is useful for us? Well, it basically tells me. You see, it tells me the following. It tells me, first of all, it tells me that Ke plus Pe equals to the total energy, right? Equals to E. And what is Ke and what is Pe? They are both. First of all, my Ke, my kinetic energy, should always be larger or equals to 0. Right? And my potential energy should also always be larger or equals to 0. So far, so good. And that tells me that, and what is my kinetic energy? My kinetic energy, again, is something like from negative infinity to positive infinity, rho ut squared dx. Right? And what is my potential energy? That's something like t from negative infinity to positive infinity, ux squared dx. We know that this guy plus this guy is always a constant, and this guy should be always larger or equals to 0. This guy should be always be larger or equals to 0, right? So it tells me that my potential, both my potential energy and my kinetic energy, both my kinetic energy and my potential energy, they are actually bounded. They're actually bounded. They should always be a finite number exactly between 0 and E. Right? Because the energy cannot be negative, right? The energy can never be negative. Okay. And this guy should always be between 0 and E. And this guy should always be between 0 and E. What is this guy? It tells me that, this tells me that, okay, overall, the speed of the string should not be too large. This tells me that overall, okay, the tension, which represents which represents the spatial derivative of U, okay, that should not be too large. Neither of the tension nor the speed of the string should be too large. Okay, no matter how it vibrates. So is that good? Okay, so this is the arguments based on the energy. Okay, and we are going to see similar things also for the diffusion. But now, why don't we take a 5 minutes break, and then we are going to resume on 15. Okay.
哦，这样好。我觉得1/2不能不要。我也觉得不能。我看到这个应该无所谓。它这个 concentration 都是因为它是 small， 不然的话，你的肉跟 T 不能 concentration， 它会变成 small vibration， 所以叫所谓那个什么。
I just have 2 questions. One was, in the case that we have the constraint bounds, do we have to integrate the infinity, or can we actually just use the constraint bounds?
You're right about that. But you see, the problem is that when T evolves, right, when the system evolves, the vibration will go further and further and further and further and further. And so, which means that no matter what bounds, finite, as long as it's finite, it's going to be breached at some time.
But because we say infinity, then we can just cut it and say that's
Yeah, because it will literally never reach that infinity.
Right. That's because they made the assumption.
Yes.
So my other question was about the tension part. Because so in a classic physics problem, when you say that energy is totally conserved, you have like a spring that's compressed, right?
Mm-hmm.
You say, okay, you have potential energy there, and then
that's right.
How high in the air does the ball go, or something like that?
Yeah.
But so it's not totally intuitive to me that the more length would be increasing tension. Because to me, that seems like if you have like a string that's X amount long, and you would be pushing it together, it would be decreasing tension to me. Unless it was something like a spring. The spring.
Yeah. Okay. So the problem is, so this is about. Okay. So I think this is about. My interpretation of the energy is that how far that you are away from its natural state or from its relaxed state.
Increases
Yeah.
potential.
Which is because when I'm further and further and further away from the relaxed state, which means that I have my motivation to get back, which should be larger. Here, the relaxed state is just that the string is at its natural position.
Right.
Okay, which is all at the 0. Okay. Now, if I pull a string, but also the most important part is that every single mass point they should exactly locate at the same horizontal position.
Mm-hmm.
There is only vertical movement that is allowed. Right. Okay. If I keep that, then you see indeed that the shape manipulating the shape. Okay, is going to increase the total length.
Mm-hmm.
Okay, then the longer the length, the larger.
So the idea is that something like XA doesn't move, right?
XA
doesn't move.
So it doesn't. Again, it only moves vertically. It doesn't move horizontally.
Right.
Yeah,
right.
it can only goes up and down, up and down, up and down. Up and down.
Okay, but there is a longer amount of string between these two than these two, right? That's what you were saying.
It is longer one. Yeah, you're right. It's okay. So the total mass stays the same, but the strain becomes longer. Right.
Okay, because of the fact that you.
Yeah.
Okay. Yeah. It's just that it's like a little bit backwards because I feel like normally with something that's
it's not a string.
Relaxed string,
Yeah,
it's
yeah,
like more like this, and then a tight string is more straight.
Yeah.
But yeah. Okay.
Okay. Cool. We're missing some people today. Yeah. Is that because of the rain?
多了，你看。这样这个东西给我什么感觉？他从头到尾做了无数的就是 approximation， 然后这个不切实际的方式，然后最后还是。但是你一个人可能会他只上下动，
不是你想就是
然后
现实生活中那些钢架桥，它就是那个铁索桥能拉起来，它把就是没有想的是有，但是我非常算。
但他这个还都可以是 approximate concept。哈，就是说有道理。接着玩不是
很厉害，你汽车上面走。
命他有 version 怎么办？他有已经掉下来。
是，让我想就是所有建筑它可能都有形变。
啊，形变啊，那懂了。你这样说有道理。
没必要太过于担心伤害。
而且你说铁索桥，我觉得真的很贴切。也是哦，一直上下的，它左右晃，为什么？因为它就是钢快，操作钢性。因为这种桥的话，就是两岸对它的一般是向岸边的拉力，还是向中间的拉力，还是说只有一个向上的摩擦力跟拉力，克服重力的，就是那个岸对它的。
Okay, let's continue our discussion. So, as I said, instead of 2.3, well, I'm going to directly jump to solving the diffusion equation on the whole line. Okay, so a general question posed for the diffusion on the whole line is the following. So first of all, the domain of my x is again from negative infinity to positive infinity. Okay, and same thing as ut equals to k uxx is the same as we have known. Okay, and however, the initial condition will be arbitrary. The initial condition, ux0, okay, that's going to be any function that's going to be 5x. And, well, can anybody remind me, why do we only need one initial condition about ux0? Why we only need one initial condition about ux0? How many initial conditions how many pieces of initial conditions did we use for vibration, for the wave equation? With 2, right? There was a phi for the initial for u, and there was also a phi, okay, for ut. So c for the psi c for ut. Why do we only need one initial condition over here? Again, it's because ut, the time derivative, is only one order. Okay. If sometime I have third order, then of course there are going to be 3 pieces of initial conditions. Okay. So this is the initial condition. Okay, ux0 equals to equals to 5x. Okay, and this initial condition is arbitrary. Okay, it's arbitrary. And when I'm saying that I would like to solve the diffusion equation on the whole line, that basically tells me that I would like to obtain what is u. Okay, I would like to obtain an analytical formats about what is xu, xt, okay, given or evolved, okay, from the initial condition 5x. Okay, so that's our goal. Well, and from now on, okay, I have set a bunch of pre-warnings for you. What I'm going to do in the next hour, it will seem to be very unnatural. It will seem to be even a little bit torture. Okay, it will seem to be okay. Why is that is so anti-intuitive? Okay, but all of that I can tell you, finally, we're going to say, we're going to see that, okay, all this suffering that we make, it is because the restriction of our level of the knowledge. That is exactly because, I mean, not until the second half, or actually the last 1/3 of this class, when we talk about the Green's functions and the delta functions, okay, if we have the knowledge of Green's function and delta functions, these things will actually be very natural. Okay. However, we cannot touch the idea of delta function and Green's function. That's exactly why we need to design a very twisted way, okay, for us to be able to go from here to deriving our final answers, okay, step by step, without any of the step, okay, to be vague. Okay, that's exactly because that we don't have a plane, okay, we don't have a plane to directly take a flight from this place to that place. So we need to go through all of the walks and the cliffs, okay, to go to that place. Okay, so before we proceed, okay, now I would like to tell something that's generally true. Okay, I would like to tell something that's generally true about linear PDEs. Okay. Specifically, I have the following four. A, B, C, D properties. Okay, for linear PDEs. Okay. The first thing is that, okay, specifically, I'm going to argue these four conditions, these four properties, okay, in the context of the diffusion equation. Okay. The first thing is that if the condition of these four equations, of these four properties are the same, exactly the same, which is that if uxt is a solution, okay, if uxt is a solution to the diffusion equation that I listed above, okay, then property 1 tells me that the translate, okay, the spatial translate of uxt is also a solution, which is ux minus yt, okay, for any y that's fixed, as a fixed number. Okay, this is also a solution. Okay, that is also a solution. Oh, probably not to. Probably I should. When I'm saying that this is uxt is a solution to the wave equation. Sorry, to the diffusion equation. I should be a little bit more specific. That I'm only referring to this. Okay, I'm not including the initial condition because of course, right? If I translate the solution from one place to another, then actually the initial condition should also be what? Should also translate from one place to another, right? And you can see the reasoning behind the translate exactly like, okay, for example, initially I have some, let's say I have a drop of water over here, and it's going to be diffuse at this place, right? And in another scenario is that there is nothing happening at this place initially, but I have a drop of water over here. It's going to diffuse and diffuse and diffuse. There's no reason that these two processes are any different from each other, except for that the place of this process, okay, the placement of this process is different. And that placement, that change of the placement is exactly called the spatial translate. Okay, I'm just simply translating from somewhere to another. Okay, from somewhere to another. X and ux minus yt. That means that everything stays exactly the same. I'm just moving my solution to rightwards by y. So that's good? Okay. This is good, right? This is actually very straightforward, right? If you have any question, just stop me because these things are not so straightforward. Okay. And the second thing is that if my ut is a solution, then any derivative of u is also a solution. Okay, is also a solution, and that exactly includes things like, for example, ux, ut, uxx, or ut, tx, that kind of things. As long as the u is differentiable. As long as my u is differentiable. Okay, And how do we see that? How do we see that? Well, and actually, probably a better way to do that is, a better way to do that is instead of writing everything on the let me try to write it on Scratch, right? So imagine that my u are really satisfied that my ut equals to kuxx. Okay, so now let's consider something that's ux. Let's say my v equals to ux, right? Then what is my vt? What is my vt? My vt is actually u, x, and t. Right? Again, we can switch the order of differentiation, okay, which exactly equals to u, t, x. So far so good. And what do I know about ut? It's actually kxx, right? It actually equals to kuxx, x. So far so good. And that is also kux xx. Right? What is ux? Exactly my v. Right? That's exactly my v. So finally, kvxx. So which means that my v is still a solution to the diffusion equation. Okay. And it may, for example, it might not be, for example, physical. That solution might not be physical because of that. Because you see, if we are talking about the diffusion of a mass, then there's no negative mass, right? Which means that my u is always larger or equals to 0. But the spatial derivative of u, it doesn't have to be always larger or equals to 0. For example, if I'm having my u to be something like this, then actually, what is my v? My v is actually something like this, right? Wait a minute. My v is going to be ux. So this place is going to be low. This place is going to be low, and then it becomes high, but then it becomes negative than this. If this is my u, this is actually my v equals to ux. Right? This is actually this part. This part is actually below than 0. Okay, it doesn't have to be completely physical, but it is still, mathematically speaking, it's still a solution. This is because this is what algebra tells us. It is still the solution to the origin, to the objects, okay, to the original diffusion equation. Okay, and you can change that. You can change that to ut or utx for any derivatives of u. Okay, and you can repeat this process just exactly by what I've done. And the core idea behind this, supporting this, is exactly that. Okay, in this class, we are entitled to switch the order of integration and differentiation as much as we want. Okay, so that's good. So this is the second point. Okay, any derivative of u is still a solution. And the third part is that a linear combination. Okay, any linear combination. Okay, any linear combination of multiple solutions is also a solution. Any combination of multiple solutions is still a solution, and that's actually not so questionable, right? It's actually what is behind the definition of linear equations. Right? Linear equations means that I have one equation and another equation, and combine them still get an equation. Okay, so if you don't trust that, then let me just expand this for a little bit. So let's say, suppose that L, don't forget the L, right? If L is sending my u to 0, right? I'm sending my u1 to 0, and L is sending my u2 to 0. Because L is linear, so my L u1 plus u2, okay, but that should equal to L u1 plus u1 plus L u2. Okay, and that is still 0. That means that my u1 plus u2 is still a solution, okay, to the origin partial diffusion equation. Okay, and the D, okay, D is actually an extension on C, because C tells you that any linear combination of multiple solutions, it's still what? is actually still a it's actually still finite numbers, okay, of solutions. But what about infinite numbers of solutions? Okay, so the answer, so the proposition for D is the following. Okay, if my uxt is a solution, then you see based on A, my ux minus yt is also a solution, right? Then, okay, for any function, g, y, okay, for any function g, y, I have literally no restrictions on this g, y, as long as it is integrable, okay, as long as it is integrable. Then my vxt, okay, defined as a convolution of ux minus y t multiplied by gy dy. Okay, this is still a solution. It's still a solution. So I just want to make sure that is that true that everybody knows what a convolution means? Convolution. Convolution. Is that true that everybody knows that what a convolution means? No. Okay. In probability theory, okay, in probability theory, you might have. So if you don't, if you still remember, let me try to remind you in the following way. Okay, so in probability theory, imagine that I have a random variable x following. And whose distribution is fx, okay, and I have another random variable y, okay, whose distribution is actually gx, okay. Then what is the distribution of x plus y? What is the distribution of x plus y? The distribution of x plus y should be exactly h, okay, hx equals to the integration from infinity to positive infinity, fx minus y, gy, dy. Right. Okay. That's the so-called convolution. That's the so-called convolution. Okay. Convolution means that I have one function and I have another function. Okay. And I will convolve them together. I would like to convolve them together. And in this case, okay, that means what? That means that you see. First of all, uxt is a solution, right? And my ux minus yt is a solution for any choice, for any of my choice of my y, right? Therefore, that means that for any choice and any number of ux minus yt, their linear combination, according to C, right? Their linear combination should be what? Should still be a solution. But now I am varying my y continuously. I'm now varying my y continuously. And for any choice of my y, the weight in the linear combination is exactly gy. So far so good? And now the linear combination is just taken in a continuum. The linear combination is now taken in a continuum. Okay, so now I am changing my y continuously. So now the linear combination becomes a direct integration. And the weight function gy now goes into the integration. Okay. I just want to make sure this part is good for everyone. Good? Any question? No question? No question? Good. Okay. Okay. So these A, B, C, D, okay, these four A, B, C, D, actually they work literally for any linear PDE with constant coefficients. As long as it's constant coefficients. And there is one more property. There's one more property I would like to add, E, okay, which that only works for the diffusion equation because of its specific form, which is that again, if my uxt is a solution, then the dilated function, okay, the dilated function of uxt, which is exactly, let's say, now I'm choosing for any a that's larger than 0, for any positive real number a, the dilation of u, okay, upon a is u square root of a x and then at. then this guy is again a solution to the original equation, to the diffusion equation. Okay, so the dialectic, what does the dialectic mean? The dialectic means that you see I have a solution. You see I have a solution u, okay, u xt, right? I have a solution u xt x and t, right? I have a solution which is a function on this haploid, at least on this haploid. Okay, for everything above, not below, I have a solution of this haploid. A dilated solution means that, okay, so now you see, how can I go from uxt to u? How can I go from uxt to this, to u square root ax and at? How do I obtain that? How do I obtain that? I first need to do what? I need to compress. It actually depends on the amount of A, right? Depends on if A is larger than 1 or smaller than 1. Okay, for example, if A is smaller than 1, that means that I first need to do what? I first need to linearly expand, okay? I first need to linearly expand my x-axis, and then linearly expand my t-axis, okay? And the ratio of the expansion is it will be exactly square root of A and A. Okay, so this guy, after the expansion on x and the expansion on t, okay, the new function, u square root of ax and square root of at, okay, that's still a function. Sorry, that's still a solution to the diffusion equation. And how do we see that? Again, let's try to do a scratch over here, right? So again, now let me say that my vxt exactly equals to u square root of a x and at. Okay. Then and if I have that, then let's say what is my vt? What is my vt? What is my vt? What is my vt? It's actually partial t of the u square root of ax and then at, right? So that's a bit? Okay. And I'm only taking the derivative on t. I'm only taking the derivative on t, which means that it's actually, okay, it's actually a multiplied by ut and then the square root of 8x and then 80. So it's a bit? So it's a bit? And what is vx? What is vx? What is vx? Now you tell me what is vx. I have already demonstrated you an example. What is vx? Okay, partial x, u, now square root of a, t, ax, sorry, square root of ax and at. Now here, I'm going to obtain what? What kind of coefficients? Square root of a, right? And then ut, the square root of ax, sorry, it's okay, it's actually us, right? And then a. So it's a good. So vxx means that I'm going to take another derivative of this, and that will produce me another square root of a, right? So there's going to be square root of a, and then square root of a, and then now uxx, okay, and then the square root of ax, and then at. Right, and I know what, I exactly know that. So this guy is A, and this guy, uxx, is exactly my vt. So that's it. So it's good. Okay. So this is the okay. So this is the dilation. This is the definition of dilation. Okay. So I have just thrown these properties to you. Okay, and as I said, you might be a little bit confused. Right? Why do we need to dive in this kind of these stuff? Okay, now why do we need to first discuss these kind of things before we are producing? We are formally trying to solve the diffusion equation. Okay, and then I can tell you that the roadmap. Okay, from now on, the roadmap will be the following. I'm now first going to present you a solution, okay, to a very specific solution, to a very specific initial condition. Okay. The first, so now the roadmap from now will be that, okay, so the step one is that I'm going to produce the solution. Okay, produce the solution from a very specific, initial condition. Okay, and step number two is that from the solution of that very specific initial condition, we are going to make up the solution to all other possible initial condition, which is my bias. Okay, this is what I plan to do. Okay, so now step one. Okay, step number one. So I am going to produce a very specific, okay, type. I'm going to produce the solution to a very specific initial condition, okay, which is that I'm going to say that, okay, Q x0 equals to 1 for any x to be larger than or equal to 0, and to be 0 to be for any x that's negative. Okay, and I would like to solve the Q xt that satisfy that qt equals to k qxx. Okay, so the new specific initial condition is exactly like this. The initial condition is exactly here. It's a step function. Okay, it's a step function. It's all zero. It's all zero for any negative x. For any negative x. And it's all 1 for any non-negative x. This is also called Heaviside, the Heaviside step function. Okay, the Heaviside step function. But that's just a name. Okay, that's just a name. You don't need to memorize that. Okay, but instead of saying that, it's actually that's something very that's something given arbitrarily. Actually, I'm telling you, it actually has a name. Okay, and we are going to see that. And the Heaviside step function is also called as hx. Okay, so now hx is a step function that is going up for one step only at 0 end, and that step, the size of that step is only 1. Okay, and it's going to be constant everywhere else. Okay, no change. Step function is such a simple and dot function, and you don't without any dot. Okay, without any dot. There is a problem. There is actually a problem when we are talking about, for example, the derivatives for this initial condition at 0, right? Because of what? Because this function is actually non-differentiable. It's not differentiable when x equals to 0. But I just say that. Okay, so I will just suggest that. Okay, we close our eyes and we ignore that. That's not an issue. Okay, we suppose that's not an issue, and let's see what will happen. Okay, let's see what will happen. Okay, so again, our goal, according to the roadmap, is that we are first going to produce the solution. Okay, for a very specific initial condition, and that initial condition is exactly given by the Heaviside step function, which is 0 for anything above 0, for anything that's below 0, and 1 for anything that's above 0. Okay, so this is my hx. Okay, this is my hx. Okay, and my argument is that I'm going to argue. Okay, I'm going to argue. My argument is that my qxt, okay, my qxt will be able to be written into a form of the function that's called something like, let's say gp, okay, where p exactly equals to x over the square root of 4kt. Okay, now confusions. Question mark, question mark, question mark, which I can see. Okay, already has. Why do we need that? Okay, why do we need that? So first of all, let me try to be different. What does the argument mean? The argument means that, you see, first of all, Q is what? Q is a 2D function. Right? Q is a 2D function. Q depends on x and both x and t. But the argument tells you that instead of the 2D function, actually Q has a much simpler form. Q can be written as a function that only depends on one variable, as long as I am relating, as long as I'm coupling x and t in the following way, such that when t grows up, such that whenever the x grows up, t will grow up quadratically, right? Because you see, when will p be a constant? When will my p be a constant? My p will be a constant as long as when I'm expanding my x, then my t also expanded, but for the quadratic amount, right? Also for the quadratic amount. Okay, so this is the interpretation, which is that I am able to simplify my solution into a one variable function. But why is that? What's the reasoning that I can do that? Right? Am I just writing that without anything backing me up? The question is the following. The question directly, the secret actually directly comes from the E over here, the dilution. Okay. You see? Now, you see, for any, as long as I am given a solution U, then the diluted function U square root of AX and AT, that's also a solution. So far, so good. And that means what? That means that, okay, so that means that, so let me do a nice expression here, okay? You see, assuming that I have already known my Q, right? Assuming that I have already known my Q. Now I already know my QXT is a solution. Solution. Is a solution, okay? So that means that for any A, okay, for any positive A, then my Q square root of AX and then AT, that is also a solution, That is also a solution. So far, so good? So far, so good? Okay. But, can you tell me what is the initial condition for Q for the diluted solution? What is the new initial condition for this diluted solution? Don't forget that my QXT actually is started from the initial condition, which is UX0, okay, that equals to this, right? It equals to this. So, what is the initial condition for this? So let me say, okay, my VXT is exactly the diluted equation. Sorry, the diluted function. What is the initial condition for VT? What is VX0? What is VX0? It's the same, right? It's the same. Because you see, my VX0 is what? My VX0 exactly, you see, my VX0 exactly equals to Q square root of AX and square root of A multiplied by 0, which is again 0. Right? But since my square root of A is a positive number, since my square root of A is actually a positive number, sorry, not the square root of A, but A over here. But A over here. Since my square root of A is a positive number, so the square root of AX will be exactly the same sign as x. And the property of the Heaviside function is that as long as two numbers are of the same sign, then their function value will be exactly the same, right? So which means that my Vx0 will be exactly equals to my Qx0. What does that mean? Well, that means that my V, the solution V, so first of all, Q is a solution, and then under the dilution, V is also a solution. But you see, these two solutions, they have what kind of property? They exactly share the same initial condition, right? Okay. Indeed, we haven't talked about anything about things like uniqueness or stability. We haven't talked about well-posedness for the diffusion equation because this actually belongs to 2.3. But if you trust, if we assume, right? If we assume that the solution to the diffusion equation is unique, what can I say? If I assume that the solution to the diffusion equation is unique, what can I say? Then from the same initial condition, what should we obtain? The same solution, right? That exactly means that, okay, if we assume, so going back to our main string, that means that, okay, that means that now taking V to be, sorry, taking V x t exactly equals to Q square root of AX and AT, okay? Taking that, because V x 0 exactly equals to Q x 0. Now, if we assume the uniqueness, don't forget, we haven't really proved this, okay? We are assuming this, but if we assume the uniqueness, then that means that my V xt should be exactly the Q xt. The solution V xt should be exactly the same as Q xt, but don't forget, V is what? V is the diluted solution. V is the diluted solution, so that tells me that, okay, so you see, that finally gives me that Q square root of AX and AT, that exactly should equals to QXT. This is exactly the property that the solution QXT should contain, okay, as long as it evolves from this specific design initial condition. You see, I have done all this route. I've done all this route to come to make my solution, okay, to have this special form. Okay, this initial condition is not arbitrary. It is intentionally designed like that. Okay, so that I would enjoy such a nice property of my solution, right? So now the question is, what kind of Q can enjoy such a property? What kind of Q can enjoy such a property? Well, that will only happen, you see, that will only happen when my T, because you see, when I am amplifying my X by square root of A, I'm always amplifying my T by A, right? That will only happen as long as my T, okay, is, and T and X, they are coupled with a quadratic relation between each other. So good? This step, so now this step is okay, right? So now it's not so weird for me to assume that, let's say, X over square root of T is a constant, right? X over square root of T is a constant. And specifically, let me use a constant, which is exactly the square root of 4k, and we are going to see that this posing of the constant is actually, it will bring us some convenience later when we are doing the computation. Okay, but the most important thing is that X and T, they should have a related, they should be related. They should be coupled to each other. Okay, with such a quadratic relation. So let's begin. So now, my argument for this was extended. Okay. Now, I know that my QXT is a function, okay, can be written as a function for only one-dimensional variable T, as long as my P is the variable that's relating X and T with the quadratic relation with each other. Okay. So now, step 1.1. My step 1.1 will be exactly, okay, how can we solve the G? Now I would like to obtain exactly the form of G, okay, to obtain to obtaining the form of G, of the GP. Okay, and well, the spirit behind this is that, you see, since originally, you see, why PDE is hard to solve, because it has 2 dimensions, at least two dimensions, right? One about x, one about t. Okay, but now you see, I am rewriting the solution as a 1-dimensional function. It only now, instead of depending on x and t independently, now the cube only depends on one independent variable, p, right? So I'm able to reduce the PDE to what? To an ODE now, and we can all solve ODE, right? So now to obtain the form of GP, we're going to reduce the PDE to ODE. How do we do that? Well, first of all, can you evaluate QT, and can you evaluate QX, and can you evaluate QXX? Okay, well, we have already assumed that QXT actually is a GP, well, my P equals to X over the square root of 4KT. Okay, can you try to compute that? Okay, within 3 to 5 minutes? Please go ahead. Yeah. Take out your pen and try to compute. Okay, what is QT? What is QX? What is QXX? Of course, in the form we should contain the form of G. Okay. Okay, so probably you have already computed at least one of it. So let's try to do this together, right? Okay, so what is Qt? How do I compute Qt? By the chain rule, that should be, first of all, G prime, right? That which is dq dg dp, right? And then multiplied by partial p, partial t, right? And I'm going to directly write down the answer, which is what negative 1/2, 1/2t, and then multiplied by x over the square root of 4kt, okay? And then g prime, which is a function of p. Okay, this is my up. And my ux, again, is going to be g prime, partial p, partial x. and this is actually 1 over square root 4kt, okay, and then g prime p. Okay, and qxx will be dqx, okay, over dp, and then multiplied by partial p, partial x, and then finally we are going to obtain, which is 1 over 4kt, and then g prime prime p. Okay, so far so good. So far so good. Okay. Well, you see, according to the fact that Q is actually Q is what? Q is a solution. Since Q is the solution to the diffusion equation, Q should satisfy what kind of PDE? My Qt should be equal to what? KQXX, right? Or on the other hand, or in another word, that means my Qt minus KQXX that should be equals to 0. Right? That's the definition of what Q to be a solution. Right? So now this is my Qt, this is my QXX. Right? So that finally will give us something like, okay, that will give us something like, okay, so that means that my 0 will equals to Qt minus KQXX, which equals to 1 over t, okay? And then I'm going to, because you see, here I have a t, here I have a t, and then that is going to be, I'm going to extract the t, and then that's going to be 1/2 p g prime p, okay? And then minus 1/4 g prime prime p. Okay? This is going to be 0. So finally, I obtain an ODE. I obtain an ODE for g, which is g prime prime plus 2p g prime equals to 0. See? Now PDE is now become an ODE. Right? This is indeed still a second order PDE, second order ODE. But if I say, let me say, if I let my f equals to g prime, can you solve this ODE? Right? That's what. That's actually f prime plus 2pf equals to 0. We all know how to solve this ODE by what? By separation of variables, right? By separation of variables. So I'm going to review the answer directly, and that will give us that fp. Okay, that will give us that fp equals to c1. Okay, the exponential of negative p squared. I'm just jumping the step. I do apologize. I don't have more time to dive in this, but I'm sure that all of you are very familiar with how to solve this ODE. Okay, so I know which is my I know what is g prime. G prime now equals to this is equals to my g prime, right? So my GP will be exactly the integration of this, or exactly the integration of this. And of course, that means that we need to introduce another constant. So now it's c1 plus, okay, now from 0 to p, e the negative p squared, okay, p, let's say p0 squared dp0, okay, and then plus c2. Okay, I'm just simply obtaining the form GP, okay, by integration. Well, now don't forget my GP is what? My GP is exactly my QXT. My GP is exactly my QXT. And therefore, the form QXT can be expressed by when I'm changing the P. There's only one thing that's about P, which is here in the integrand. Okay? And everything in this interval that's only serves for this interval. Okay? And it doesn't have to change. It doesn't have to be replaced. So now that equals to C1, the integration from 0 to x over square root of 4kt. That is exactly the definition for p, right? Okay, and then e the negative p. Well, okay, I will just for simplicity, I'm going to just write it as e the negative p squared and dp, and then plus c2. This is my qxt. Right, and indeed, my C1 and C2, they are still undetermined. But how do we determine C1 and C2? How can we determine C1 and C2? How do we determine that? Don't forget, we still have one thing that we haven't utilized yet, which is the initial condition, right? We still haven't utilized our initial condition yet. So that means that you see, when t, because uqx0 should be what? Should be the limit of qxt when t goes to 0, right? So what I'm going to do is that now in this formula, I'm going to take my t goes to 0. I'm going to take my t goes to 0, and let my x to be positive or negative, and let's see what will happen. Let's see what will happen. Okay. So now let's say, okay, when x is larger than 0, then my qx0 is actually what? What was the initial condition? When x is larger than 0, is 1, right? That is 1. And that is what? That's actually c1. Now you see, in the integration, I was integrating from 0 to x over the square root of 4pt. X is a positive number, and that is fixed. But t is going to 0, so this guy will go to what? Infinity, right? This guy will go to infinity. So this is going to be from 0, integrating from 0 to infinity, e to the negative p squared dp plus c2. Okay? Do you know how to integrate? Do you know how to do this integration? Well, of course, you have learned probability, right? This is just like integration of what? Of a Gaussian distribution or normal distribution. Well, okay, normal distribution. This is the first time in this class that we have talked about normal distribution. Okay, in this lecture. Okay, and then you're going to see what I'm going to show you that the normal distribution or the normal function is everything about the diffusion. Diffusion is indeed the normal distribution, and expanding distribution, and normal distribution whose variance is becoming larger and larger and larger on time. Okay, but now let's try to keep going. And now I'm going to directly review the answer. The integration is exactly the square root of pi, the square root of pi over 2. The square root of pi over 2. Okay, c1 and then plus c2. Okay, and then same reason, when x is smaller than 0, then my qx0 is going to be what? Now it's going to be what? When x is smaller than 0, this is going to be 0, right? This is going to be 0, and this will equals to c1 and the integration from 0 to negative infinity, e to the negative p squared dp, okay, plus c2, and this will equals to negative square root of pi over 2 c1 plus c2. Okay, so now you see, what do I have is 1 equals to square root of pi over 2 c1 plus c2, and 0 equals to negative square root of pi over 2 c1 plus c2. Right, just two variable order 1 linear equation. Okay, and it's not so hard to see that actually my c1 equals to 1 over the square root of pi, and my c2 equals to 1/2. My c2 equals to 1/2. And finally, that means that my qxt, I'm now giving directly, okay, an analytical formula for the solution of q. Okay, qxt now equals to 1/2 plus 1 over square root of pi. Okay, and then is from 0 to x over the square root of 4kt, okay, e to the negative p squared dp. Let me try to review what we have done, okay, over here. In the whole step 1, this wraps up step 1, okay. This wraps up step 1. This is end of step 1. You see what we have done. Let's try to conclude what we have done in step 1. In the step 1, we first of all started from a very specifically designed, okay, initial condition, which is the Heaviside step function. Okay, the Heaviside step function only goes up for one step from 0 to 1 when x equals to 0. And everywhere else it stays constant. This is the definition of the Heaviside step function. Okay, and we propose to look for the specific solution of the diffusion equation if the for the initial condition as the Heaviside step function. Okay. And we realized that, later we realized that the solution Q, it should have a very specific form, such that instead of depending on x and t independently, actually it can be reduced to a one variable function, which is my GP. And my P indicates the relation between x and t, which is a quadratic relation. Okay, and we are having the reasoning behind this reduction is that because due to an earlier property that we have derived, right? As long as my Q is a solution, then a dilated version of Q, which is my Vxt, that's also a solution. And then we found that the Vxt and Qxt they actually exactly share the same initial condition from the Heaviside function, right? And as long as we're assuming the uniqueness of the solution, then we can just say that my V and the Q, they should be exactly the same. It should be exactly the same, okay? And that means that the Q, after the dilation, they should be the same. That's the source, okay? That's exactly the reasoning behind the coupling between x and t, okay? And as long as we can simply reduce the qxt to a one variable function, gp, then we are able to reduce the PDE to an ODE. In my step 1.1, to obtain the form of G, we are reducing the PDE to ODE, okay, by directly compute Qt, Qx, and Qxx in the form of G. Okay, and as long as my Q is a solution, then finally I can all of the solution I am able to obtain, right? I'm able to obtain what is the first of all, what is the form of G, and then what is the form of the Q. Okay, so this is the route. This is the route for my step number 1. Okay, I might not have enough time to complete step number 2, but I would like to remind everyone. So what did we say? So you see, we have talked about all these properties for U, right? A, B, C, D, E. We were using, well, you see, we have been using E a lot in our step 1. Now let's say, well, now let's say property B. For property B, you see, if U is a solution, then any derivative of U is also a solution, right? Okay. I have already known that Q is a solution. Of course, Q is a solution coming from a very specific initial condition, but the same argument should hold for Q, right? Any derivative of Q should also be a solution, right? And instead of asking you to go for an arbitrary derivative, can you please tell me what is the following derivative, partial Q, partial X? What is that? What is partial Q, partial X? We can do this together, right, to review this exciting finding, right? Partial Q, partial X. First of all, 1/2 will go away, right? What about the rest? What about the rest for partial Q, partial X? I am trying to taking the derivative of but the function is in the form of integration, right? But luckily, the variable is only in the integrand. It's only in the integrand. So first of all, we'll be first of all the 1/√pi, okay, that will stay, and then e the negative p squared, okay, this will stay, but as long as p equals to my x over square root of 4kt, right? And then one last thing is exactly the the partial x over square root of 4kt and partial x, right? This is partial q, partial x. And finally, this is the square root of, okay, this is the square root of 2 and square root of pi kt, okay, and then e the negative x squared over 4kt for any t that's starting at 0. For any t that's starting at 0. So again, according to the second problem, Q is a solution. So partial Q partial X, that's absolutely should be a solution. And what is the shape like? What kind of function is this? What kind of function is this? What kind of function is this? Exactly, that's our bell curve, right? That is exactly our bell curve. That is exactly our bell curve that, okay, and it's a Gaussian function, right? It's a Gaussian function, bell curve Gaussian function. Okay, and what is the sigma of this? So if this is a distribution? Okay, if this is a distribution, what is the variance of this Gaussian distribution? What is the variance of this Gaussian distribution? It should be x squared over 2 sigma squared, right? It should be x squared over 2 sigma squared, right? So so that means that my sigma squared. Okay, I don't know what sigma squared is, but if that's something that can be defined, my sigma squared should be 2kt. So what does that mean? And don't forget, what is the integration of that? What is the integration? So let me call this guy to be my sxt, okay? To be my sxt. What is the integration of sxt when from negative infinity to positive infinity, let's say, for dx sxt? What is the integration for that? Well, it's actually very easy to see that that's actually 1. Right, that's actually 1. So it can be indeed, you see, because first of all, the integration from negative infinity to positive infinity, I mean, as long as my t is fixed, okay, as long as my t is fixed, okay, this function, the integration of this function, first of all, it integrates up to 1. And second, my sxt should always be a non-negative number, right? Should actually be a non-zero non-negative number. Because of what? Because you see, my t here, this guy is larger than 0. This guy is also larger than 0. But it's always a non-negative number. So, which means that my sxt is indeed, it can serve as a distribution function of a certain random variable. Okay, and this function, and this random variable, okay, this random variable will be exactly a x, let me use xt to represent that, will be exactly a normal distribution, okay, whose expectation is 0 and whose variance is exactly 2kt. So what does it mean by this? When t becomes larger and larger and larger, the sigma of this distribution, or the variance of this distribution becomes larger and larger and larger. That means that, okay, initially, when t was small, initially there was a bell curve, right? But most of the probability mass was concentrated around 0 because the sigma was very small, right? But when t becomes larger and larger and larger and larger, the bell curve becomes wider and wider and wider and wider and wider, right? So this describes the process of the diffusion. And you may wonder why we are specifically interested in what is partial q, partial x, right? Oh, sorry, why we are specifically interested in this, okay, derivative of q? Well, the reason is the following. Let's recall that, you see, what is my q? My q is this, right? This is my q. Sorry, this is my q qx0, right? Can you tell me what is sx0, which is exactly partial qx0, partial x? Okay, I know it's very hard to describe it, especially when x is 0. But what would happen when x is not 0? What's the derivative? What is the derivative of q when x is not 0? What is the derivative of the Heaviside function when x is not 0? 0. Here, 0. Right? But what can you say about this guy? This derivative. So you see, if I'm talking about, so that's it, because the derivative is based on what? The derivative can be naively, a very naive description is that derivative can be regarded as the limit, okay, the limit of dy of delta y over delta x. Right? In this case, it's actually, so here, let's say I'm jumping from here to here. Let me zoom in up, okay? I'm jumping from here to here, okay? And I'm letting this is my delta x. This is my delta x. And I am letting my delta x to become smaller and smaller and smaller and smaller, but the delta y is always what? Delta y is always 1. So this guy, so the derivative, okay, so we know, so now we know two things. So now we know two things about the Sx, okay. The first is that, okay, the first thing is that the Sx is exactly 0, okay, for any x that doesn't equal to 0. And secondly, the Sx0 will be exactly infinity, positive infinity, when x equals to 0. So which means that the shape of the Sx, okay, the shape of the Sx, don't forget, my Sx is the initial condition, for S, okay, for Sxt, okay. This guy will be exactly something like this. This is my Sx, 0, this is my S. It's going to be 0 everywhere else, okay, but it's going to be infinitely. It's going to be an infinitely large number, okay, at 0. And it also has a property that the integration of Sx0, okay, from negative epsilon to positive epsilon dx is going to be 1. This is because of what? This is because Sx is defined as the derivative of the Heaviside step function, right? So when I'm integrating back around 0, it should recover this exactly step, right? So how do I interpret that? How do I interpret my Sx? So my Sx can be interpreted as, again, if I'm saying my Sx is the distribution of certain random variable. How do I interpret that random variable? All the mass, you see, the mass of a random variable comes from what? Comes from integration, right? And this tells me that all of the mass exactly locates at x equals to 0. What kind of random variable has the property that all of its probability mass locates exactly at 0? That is exactly a constant random variable. A random variable that will always give me a fixed number, 0. A constant number, okay? Only a constant number will give me that kind of distribution. And that also means that initially I have a drop of water, but all of the mass, okay, all of the mass exactly locates at this place, nowhere else, nowhere else. It only locates, all of the mass only accumulates at one point. All of this only accumulates at one point. And then when we go some time, I know that my Sxt, okay, equals to the square root of 2 pi kt, okay, e the negative x squared over 4 kt. That means that now when my t becomes positive, okay, so for example, if my t is a very small number, then the shape of my Sxt should be something like this, right? When my t is small, and then when my t becomes larger, I'm going to have something like this, right? And even larger, my t is going to be something like this. Forgive my drawing, but what you can imagine is that a group of the Gaussian distributions that's I mean initially all probability mass accumulates over here and gradually goes down. Okay, this exactly depicts the process of the diffusion. Okay, that if one thing, if initially all the mass stays at one point, then what will happen next? Okay, so I probably have to stop here, but this is exactly the most important information I want to give you. And in the next class, we are going to complete our stepping out. This is a very important physical interpretation. Okay, this is a very important physical interpretation. And you can see that. So in the next class, we'll first finish step 2, and then we will try to relate this picture, okay, to random walk. Okay, to random walk. That which means that which means that random walk is the following. If initially I'm drunk. So every step I will go left or go right, but But every step I'm just going for one step. Okay, I go right, I go left, or go left, or go right, or go right. Okay, so you see initially my place, my location is fixed. I'm only at 0, right? But after some time, I can be in many places. I can be in many places. Then what we see is that, I mean, when time evolves, the place of the drunk, okay, the probability mass of the drunk, okay, will be exactly evolving as a diffusion equation, and will exactly looks like, okay, the Gaussian distribution. Okay, this is what we're going to do in the next class. And thank you very much for coming today. I'm going to release the homework for chapter 2 later today, but it will not due next week, but it will be due in 2 weeks from now. Okay, thank you very much.
现在就关了，我好像有个
Yes, go ahead.
One question.
Yeah.
So on the homework 13.2.1, see, I see what I have to go with it. So this is the this step here. I sort of know that this is what it used to look like, but I don't know why I can do that.
Let me see. Okay.
And that is agreed, which means that this equation
Show that as a constant. Okay. And I suggest the following. I suggest you try to first do this with a one-dimensional version. Okay. And then see what you can use.
Okay, so you're saying there's only, I don't really know.
Yeah, assuming this is a one-dimensional version.
Okay.
And then see if you can do this by individual parts. Okay. If you can do this by individual parts, then individual parts plus the boundary condition, which is actually a very specific case for the Stokes theorem. Okay, and then later with the Stokes theorem, we'll be able to solve these three-dimensional problems.
Because this is even pre-integration that I think is where I'm confused. The integration part is sort of easy.
Okay.
It's this step right here. You have the gradients inside. And I know that you need this inside, so you drag the gradient out. But I don't really understand how this. I know this has to do with the kinetic energy, that's what I said. But I don't really know why I have to do that. Then how this turns into this.
Again, what can you do what can you say for the one-dimensional case? So you see here, if that's the one-dimensional case, then this is calculated with this guy and this guy, right? Okay. So if everything is one-dimensional case, then what is that? This is actually 5 prime multiplied by. So okay, so that's actually something like. So in the one-dimensional case.